All right, hi everyone. Welcome to our little experiment with Unit 6 on radical functions. So we decided that you guys deserved a little break from the norm, and we decided to switch things up where you're going to watch these lessons at home and then work in class together and with your teacher on some of the practice problems and examples that you would have otherwise done for homework. Just like in our other units, we kind of want to introduce this by relating it to stuff that we've done in the past, and also talking about the types of graphs that we're going to see and the various behaviors of those graphs so that you can pick them out when you are asked to analyze them on your future tests. So what we're going to try to do, and if you have some at home, we're going to draw two graphs in hopefully two different colors. First, we're going to go back to what we know about our quadratic function, just the parent function y equals x squared, and we're going to plot some points to make that parabola in red. After that, we're going to look at what the inverse of that is going to come out as. All right, so remember that making a table is simply plugging in those x values and getting the resulting y values to form a point on the curve. So when we plug in -3 for x into the equation y equals x squared, well, -3 squared is simply 9. So we'll continue to fill out the table that same way. -2 squared, +4, -1 squared is +1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So those are the basic points that we're going to use to plot on our graph and get this parabola. All right, and hopefully that looks very familiar to us all as we've spent a lot of time on that. All right, now let's try to switch color pencils and draw what the inverse would look like. And if you remember what an inverse is, it's when we switch the x and the y. So we really don't have to do anything in terms of plugging in. We're just going to take the same table and switch the values of x and y in that quadratic to fill in our inverse table for what will become a new function that we'll learn about in this unit. So in our first row, we saw that -3 was the x value and 9 was the y value. And so we're just going to switch that. Put 9 in as x and -3 as y. And it's simple as that, so you can go ahead and fill in the rest of the table in the same way. All right, so now we've got all of those points filled in. Remember, those are just ordered pairs. We're going to plot those on the graph to get a new function, or maybe we shouldn't call it a function yet, and see how that compares to what we have already on our screen. Okay, so excuse my not so exact drawing there, but we get kind of what looks like a sideways parabola. And what we want you guys to notice is that the two graphs actually do intersect. And hopefully you can see that there are two very distinct points of intersection. One right here at the origin, and one right here at the coordinates 1, 1. Now what's special about these 2 points is that that's where the x values and the y values are the same. And that's going to happen each and every time we graph a function and its inverse. So when we answer the question, why is the intersection here? It's because this is where y equals x. And that, if you remember, is the line that goes through the origin with the slope of 1 that serves as the line of reflection for a function and its inverse. All right, now look at this blue graph here, and hopefully you can tell that this is something that would not pass the vertical line test. If you remember, if it doesn't pass the vertical line test, then we would say it's not a function. This vertical line crosses that graph twice. So in this question here, is the inverse graph a function? No, it's not. However, what we're going to do to make this something that we can analyze as a function is we are going to actually look at just the top half of it. And the top half that we get is going to give us the square root function. So our summary and conclusion is going to be stated as the inverse of the quadratic function is the square root relation. Okay, and again, we're not going to call it a function yet until we take away the bottom half of this, half of the sideways parabola, and at that point we will be able to call it a square root function. So let's just make a little note of that. The top half is a function, and its equation is simply y equals the square root of x. And that is what we're going to study as the square root function. All right, we're going to do the same thing now looking at our good friend from last unit, the cubic function. So let's go ahead and plot these points, again, by plugging in these x values for x into the y equals x cubed equation, getting our y values and plotting them. So again, negative 3 cubed, when we calculate that gives us a negative 27. Because 3 as an odd power makes sure that the negative input results in a negative output. Same thing with negative 2. When we cube it, we're going to get a negative 8. Negative 1 cubed is going to equal negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. And 3 cubed is 27. All right, a couple of these points obviously are not going to fit on our graph so well, but we'll plot what we can and see what shape that hopefully we can kind of view as familiar. So let's start with negative 2, negative 8. Negative 1, negative 1. 0, 0. 1, 1. And 2, 8. And if you remember this guy, it kind of looked like a stretched out S-curve that went through the origin. That was our parent function for the cubic. All right, I want you guys to take a second using a different color and fill out what the inverse would be and then plot those points. All right, good. I hope we got a chance to fill those out. And again, all we did was switch what we had previously that was in the x column to become the y column and what was in the y column to become the x column. So nothing in terms of extra work really happening there. When we plotted it, again, there's only a few of the points. We couldn't get to the negative 27s on our graph, but the ones that we did plot, again, we see that there's this kind of reflection from our red graph to our blue graph, giving us the inverse. Notice that we do have points of intersection again, and those are where x and y are the same. Again, lying on that line, y equals x. Every point on that line is where x values and y values are the same. So in answering those questions, we see we got a lot of similar answers as last time. Where do the parent function and the inverse function intersect? Now we have 3 points, negative 1, 0, 0, and 1, 1. Why do they intersect there? That's because, again, these are where the values of y equal the values of x. Now this time, let's look at that blue function, and I'm calling it a function because what test does it pass? It passes our vertical line test. Anywhere we draw a vertical line, we will not cross the graph more than once. So when we answer the question, is this inverse graph a function, you can now say yes. So just like last time, we wanted to give this function a name. And remember that it came from the opposite of our cube function, y equals x cubed. So now, the cubic function, inverse, is going to be called our cube root function. With the equation y equaling the cube root of x. And notice the little bit of difference here. When we talk about the different radical functions, that number that represents the type of radical we're working with is called the index, and it's going to be written as a small number inside, or right outside, I'm sorry, the radical symbol. All right, so now that we've talked about these inverses for a little bit, just by looking at the graph and switching x and y, let's practice when we're given the equation. What I want you guys to notice is that our original equation has a certain type, and that can help us figure out what type of equation its inverse will be. So looking at this first equation, number 1 here says y is equal to x squared minus 4 all over 7. What we hope you guys recognize is that this term x squared means that we have a quadratic function. And what we learned on the last page in graphing the quadratic and its inverse is that we should see a square root as part of the inverse equation. Now, remember that when we come up with an inverse, it is merely about switching x and y, and when we have an equation, we now want to solve for y. So switching x and y tells us our equation is now going to look like x equals y squared minus 4 all over 7. Not that side. There we go. Okay, we want to get y by itself. The first step, if we peel the onion, we want to get y by itself and isolated. We want to multiply both sides by 7 to give us 7x is equal to y squared minus 4. Next, we want to add 4 to both sides, leaving us with 7x plus 4 is equal to y squared. Now we're at a step that we've been dealing with quite a bit recently. How do we get y by itself when it has a square? Well, to undo a square, we know we want to take the square root of both sides. And when we do that, apply that to our equation, we have to tack on this plus or minus to make sure both the positive and negative parts of that equation are included. And that goes back to why we got 2 halves to that sideways parabola back here on the first page. So flip back and let's look at this real quick. And we see that this really represents y equaling the positive square root of x, while this half that we're going to ignore when we look at it as a function is our negative square root of x. So individually they're functions, but together they gave us something that wasn't. And that's why when we look at the inverse of this quadratic, lots of pages here, we're going to see a plus or minus in our answer. So our final answer for this one is y equaling plus or minus the square root of 7x plus 4. And what we see here is that it is a square root relation at this point because the plus or minus is there, meaning it is not a function. All right, I'm going to pause a second, and I want you guys to try the other two on your own. Similar in how we want to switch x and y and solve for y, but a little bit different process in getting those y's isolated. So take a minute, pause your video, and we'll come back and talk about our answers. All right, guys, let's take a look at what we should have at this point. If you look at what we did in number 2, what we want you to realize is that we see an x cubed in this problem, which means we have a cubic function. And switching x and y, we get x equals y cubed plus 8. Then we want to subtract 8 on both sides, leaving us with an x minus 8 equals y cubed. Now here's the most important part, and this one may be a little bit new. We need to get rid of the cube. That power is a 3 now. So undoing the square root, or sorry, using a square root wouldn't undo the cube. So we have to use a cube root. You can see that's going to cancel out our power of 3, leaving us with just y. Cube root applied to both sides. This one does not need the plus or minus because it's an odd root. So our final answer is simply y equals the cube root of x minus 8. Now remember that the cube root is a function, so we'll write the type as cube root function. Now I started to work this one out, but I stopped right after switching x and y so we can do this one together. Here we have to get rid of a square root eventually. So we're going to treat this one a little bit differently, but I hope it makes sense given what we've done so far. All right, again, we're going to want to isolate y, so we subtract 1 from both sides, leaving us with an x minus 1 is equal to the square root of y minus 5. Now, unlike the last two problems where we had to get rid of a power, now we have to get rid of a root. So again, these things are opposites. So if I want to get rid of a square root, I'm going to square both sides. And that will knock out my radical. All right, what we're left with is x minus 1 is equal to, x minus 1 squared is equal to y minus 5. Last step we want to do is add 5 to both sides. Now notice, this square around the parentheses is not letting us combine any terms, so we're going to leave that x minus 1 by itself inside the parentheses squared, and the plus 5 has to be on the outside. So our final answer is y equals x minus 1 squared plus 5. Now, remember, when we see an x squared as our highest power of x, that means we have a quadratic function. And that's a good thing because what we want to see is that the inverse of a square root gives us quadratic, just as the quadratic inverse is a square root. All right, hopefully that makes a little bit of sense and puts it together when we see the different types of equations and their resulting inverses. So now what I want us to do is, just like in every other unit, we want to make sure that we have a good understanding of these graphs and that when we see them, we can explain things about their domain, their range, intervals of increasing, decreasing, etc. So let's talk about our square root function. Notice that there's no plus or minus here. This is just the positive square root. So we're going to see that this is half of that sideways parabola that we graphed in the first part of this note packet. Now, tell me about plugging in a value like -2 in for x into our square root. F of x equals the square root of -2. Or I should say f of -2 is, and that's the answer we're trying to get. However, you should tell me when we take the square root of a negative, we would get a non-real or imaginary answer. So this is not going to come up on our graph. So when you graph this on your calculator too, you're going to see an error or a non-real result. So we won't have any input for x's that are to the left of 0. Our first point on this graph will be where x equals 0. Plugging in 0, we get the square root of 0 equals 0. Plugging in 1, we get the square root of 1, which is 1. I jumped to 4 because that's a perfect square. When square rooted gives us 2, and when we square root 9, we get a 3. Again, no plus or minus there, so we don't have a plus or minus answer, just the positives. Plotting these points, we get that top half of the parabola that we saw on the first page. Here is our square root function. It's a little bit different than functions we've seen before, but if you remember from the beginning of this school year, we talked about how it was special given that it had that endpoint that no other functions that we talked about have. So, first things, x-intercepts or zeros are solutions. In this parent function, we only see one, and that's at the origin. It's the only time it's going to cross the x-axis unless we've moved it. Same thing with the y. The only point that it's crossing on the y-axis is 0, 0 as well. Domain. This kind of goes back to what we talked about when plugging into the table. We can't plug in negative numbers into a square root. We'll get something imaginary. So we don't want anything imaginary to show up on our graph because it won't. We have to restrict our domain to all numbers, including 0 and higher. When we take the square root of those positive numbers, we're going to get positive numbers. So therefore, the range is also going to be from 0 to infinity. Notice it's above the x-axis the entire time. All right, now looking at intervals of increasing. When we start at that very beginning of our function's graph at 0, 0, and we walk along it from left to right, it looks like we're walking uphill the entire time. This thing does not turn around and change directions. So our increasing interval is the entire domain, starting at 0 and never stopping until infinity. You can see because that's true, we're never decreasing on this graph. All right, now finally end behavior. We've talked about this before, but usually we have 2 blanks to fill in. In this one, we're only asked about what the right end is doing, and that's because there is only one end with an arrow, and that's the one that's pointing right. What we'll see is that as x goes to infinity, or right forever, that the f of x, or the y values, will go up forever to infinity. So even though it looks like it's kind of going pretty slow and it's pretty flat, it actually will increase forever and ever, and therefore the y values will approach infinity. All right, real quick, we'll go through and do the same thing with the cube root function, and then we'll talk about the basics of transformations on both of these. Same thing, we can plug in numbers here to get the y values that we can use to plot. Notice in this case, we can use negatives inside our cube root function. The cube root of -8 gives us -2. The cube root of -1 gives us -1. The cube root of 0 gives us 0, and the cube root of 1 gives us 1. The cube root of a +8 gives us a +2. Plotting these points, we get this sideways S-curve again. Giving us this shape. So unlike its square root friend, this guy does not have an endpoint that goes on forever in all directions. All right, x-intercepts, zeros, and solutions. We see again that this thing, because it's a parent function, goes through the origin. So 0, 0 is where it crosses the x-axis and is the time that it also crosses the y-axis. The domain. So again, we see arrows pointing left and right forever. The domain is all real numbers, negative infinity to infinity. The range, also sneaky like it's the square root function, doesn't look like it's going to get very much higher, but it actually does. And the range reaches all real numbers as well. So this one is a pretty easy function to talk about its domain and range with, because the domain and range is always all real numbers. All right, increasing, starting from the very left. If you're walking along this curve, you are actually always going uphill. So we're increasing forever, negative infinity to infinity, its entire domain. And if we're always increasing, then we're never decreasing. Okay, so last thing we want to talk about, end behavior. Again, this one's a little different. It does have 2 arrows. So we are going to talk about what happens on the left end as x goes to negative infinity. Right here, we can see that as x goes left, y is going to go down forever towards negative infinity. On the right arrow, as x goes towards positive infinity, we see that that arrow is going to have our y values approach positive infinity as well. All right, hopefully that's not too much of new material there. We've talked about those concepts before in other functions, and we'll see that those are some similar characteristics we'll continue to use in our study of functions throughout the year. Last thing we talk about with functions is when we want to transform them, when we want to say how these things have been moved from the parent functions that we just graphed. So let's recall that when we see a positive or a negative sign, this tells us which way the function has been reflected. If we see a negative, we know that's been reflected down. All right, when it's positive, that's the normal, where it's reflected or oriented upwards. The a value on the outside tells us if we either move this function to make it skinnier, which means stretched, or wider. Wider happens when a is a small number, so between 0 and 1. Skinnier or stretched happens when a is a big number, or greater than 1. And then finally, we've got our 2 friends h and k, which we hopefully remember h as being the insider that lies. This tells us if we've moved right or left, and k tells us if we're going to move up or down. So, same type of thing we've talked about before. Now, instead of parentheses or absolute value bars, we're just going to use those radical signs as what dictates inside versus outside the function. So let's take a look at the first 2, and I'll have you guys work on the rest. So in number 1, we see x minus 2 plus 5 on the outside. Minus 2 represents our h. And because insiders lie, that means we've moved right 2. And outsiders are plus 5 here. Tells us that our graph has been moved up 5. Actually going to skip down and do a different one that has an a value and see if that is something that we can work on together so you guys can try the rest on your own. Let's take a look at number 6 here. Number 6 says y equals 1/2 times the cube root of x plus 1 plus 4. I see 1, 2, 3 numbers here that are going to apply to the transformations we're going to list. Let's start with the easy stuff, that plus 4. That plus 4 is our k. It's an outsider that doesn't lie. We've moved up 4. This plus 1, however, is an insider. It's inside that radical, the cube root, and therefore is going to lie to us, telling us that we're going to move left 1 unit. Lastly, this 1/2. This is a small a value. This number has made our graph wider because it was being multiplied on the outside of the function. If you graph that in your calculator, you're going to see that the graph you get is a flattened out version of one that we've graphed previously. All right, so you guys know how to do all this stuff. You're super good at it. We're going to let you take it from here. Pause your screen and we will check your answers in just a moment.